Mhm. We have discussed about the most strict law in the world about privacy protections. But however, data mining and privacy protection is not a zero-sum game. They share the same ideal of promoting the development of our digital economy. So we can actually build a win-win cooperation by technology means. And also definitely the law brings new opportunities and new scenarios for the application of all this data security and privacy protection technologies. So one of the technology that I really want to mention is privacy preserving computation. So it has been proposed in recent years, which refers to the technical system that explore the value of the data on the premise of providing privacy protection. Because there's a lot of data processors or other attackers who intend to steal the information. So privacy protection computing technology can actually put data calculation in an encrypted or transparent state. And also this concept does not refers to a single technology. It is a set of different technology. It's a combination, including artificial intelligence, cryptography, data science, and many other fields. So here we can see a structure about the privacy protection computing. So it can be basically break down into three parts: the data owner, the calculation party, and the result recipient. So first, we got the data owner, where it transmit the data to the calculation party, where they do the processing. And then the result was being sent to the result recipient. And also, usually in a scenario, in order to increase and reach the dimension of our data resources, there should be at least two participants where each participant can take one or more roles. And also we can see there's 1 to 7. So all these numbers means the risk point in the structure. So for 1, 5, and 7, they are the risk of data storage of the owner, processor, and the recipient. And for 2 and 6 is the risk of transmission of data. And for 3, it's the process risk of data while calculation. And the fourth, and for 4, it's the result risk of data after calculation. So these days, the privacy protection technology in like data transmission, which is 2 and 6, and data storage, which is 1, 5, and 7, is relatively mature. It is like the company that do not want to increase their costs, that they do not use this kind of technology. So that's why we need, you see, law solutions. So basically right now for technology field, they are focusing on 3 and 4, which is the privacy protection calculation, focusing on the process and the result of the data mining, as I listed on the right, process and result. And for the protection of process, it means that it's difficult for the processors to obtain additional information besides the calculation result. And for protection of the result, it means that it's difficult for the result recipient, after they got the result, to retrieve the original input and all the privacy information based on the result. So right now, there's this 5 technology in privacy preserve computation that are really hot. The first one is federated learning. The second one is secure multi-party computation, or SMPC. And the third one is confidential computing. And the first one, differential privacy, or DP. And the fifth one, the homomorphic encryption. And also, I kind of, also the chart on the right kind of shows the effectiveness of the all these systems on both process and result protections. So also you can see there's more, like on the fifth line, I wrote LDP, which is local differential privacy. It's like a small branch of DP. And for the last one is full homomorphic encryption, which is like, because homomorphic encryption usually breaks down into partial and fully homomorphic encryption. So here I list the FHE. So let's talk about all these technologies in a little bit more details. So for federated learning, it was originally being the first one for the first system. It was originally being proposed in the field of machine learning. Its core idea is that the participants tried their best to first do the computation of the model locally, while they only communicate and interact with each other when the model needs to be updated. So at present, there's like the security of this kind of system was not provable in the academic field. And also, in fact, all kinds of federated learning systems are difficult to actually generate a zero information leakage during the model updating. So using the federated learning system, sometimes it might leak more information more than the final result. So it's not worthwhile. And also, although the communication loss of the federated learning is lower than the second technology, the security multi-party computation, its performance is also largely restricted by the network bindwise and delay and other factors. And for the second technology, it's the security multi-party computation. So it was a really good technology. I first give this kind of conclusion, because SMPC's provable security, and also in addition to the final result, there is no information leakage to this system. So it was really favorited by cryptographers. And SMPC contains a really complex cryptographic operations. So the implementation of SMPC needs to pay a really high cost, but it's worthwhile because it's really secured. And for SMPC, in some situations, with a really low complexity, such as maybe the SMPC is protecting linear models, then SMPC can really achieve an acceptable effects. But when computing like complex scenarios, such as maybe a neural network, the performance of SMPC is still poor. So the bottleneck of SMPC is mainly the communication time, like it's really costly, and also its progress it's not only depends on the breakthrough of the series behind, but also restricted by the network bindwise and delay. And then the third one is confidential computing, which compared to the above mentioned two, it's different. Like the first two is decentralized systems, but for confidential computing, it is gathering multi-party data sets to actually centralize. So except for the hardware, it is not different from the original data computing. So it does not have algorithms or network bottlenecks and has a really strong performance. So basically, the core of confidential computing is the hardware-based trusted environment. But however, if the companies wanted to deploy a hardware-based trusted environment, they need to purchase specific hardwares, which will definitely increase the cost significantly. And then as the fourth is differential privacy, or DP. So the protection goal of differential privacy is actually the calculation result. As you can see in the chart on the right, it's the fourth line. Like it only protect the result. It cannot protect the process. So it's fundamentally different from the above three systems. So taking machine learning models as an example, the differential privacy can add a certain amount of noise to the model result to ensure that it's difficult for attackers to retrieve the sample information from the result. But however, since they need to add all this noise, they definitely need to have an explicit access to the training data. So that's why it cannot protect the process of the training. And also, since like they need to add a noise, there's this kind of error. They will add a certain amount of error to the system, and that was non-negligible. So usually it is feasible for some scenarios that are not sensitive to the accuracy of the model, but it was not acceptable to like risk recognition or face recognition, which in these scenarios, they have a really high accuracy requirements. So it also is, there's a few limitations to this technology. And I want to mention a little bit more about the branches, like a small branch of the differential privacy, which is local differential privacy, or LDP. So unlike differential privacy, which only add noise to the result, local differential privacy already add noise before the calculation process. So you can see on the chart that it both protect the process and the result for LDP. So therefore, local differential privacy can protect the process and the result at the same time. And also, but on the flip side, since it add error before the calculation, so definitely it bringing more error compared to DP to the system. So the problem is that data processed by LDP can only support limited statistical calculation at present, and definitely cannot support complex scenarios such as machine learning models. And then it's the fifth is the homomorphic encryption. So this topic, so for homomorphic encryption, it can break down into partial homomorphic encryption, which are usually which is kind of only a support to other systems. Like for partial homomorphic encryption, it can only support a limited ciphertext computation depth. So it is often applied as one of the components of other systems. And also for the fully homomorphic encryptions, right now it is only at research level. There's still no commercial cases yet. So basically we discussed about other technology solutions. And then we think a little bit more to the future. Like the future brings us both challenges, but also since the development of our technology and our law solutions, we can definitely find new solutions to all these challenges. So the new challenges are definitely, I believe, in the future for our society, we might have this open sharing of our public data. Like countries might build and establish a standard and unified public statistical system, which is a centralized and unified public database, which is good for interconnection and sharing of public data for application systems. And it will be a really good infrastructure for the development of our digital economy. But however, since all like people's data are being protected in a public database, then it definitely we need to lower down the risk, and we definitely need to increase the security levels, because the cost of being attacked is so high. So this brings our new challenges, which is to bring the risk of being attacked at a really low percent, even lower than the right now situation, because there's so much data in the future stored in this public database. And the second thing is also like in the future, there's definitely will be specialized database. Give me an example, like each field for maybe health and medical care, there will be this cross-region database that will be built because in this database, like technologies such as virtual integration and edge computing can be able to apply to improve the efficiency of all those databases. But also again, as the public database, since people's information are being stored at the same place, the security must be really high, like both for the transmission of the data and the storage of the data. So that brings to our future solutions, which is like the integration of data elements, like using the above mentioned technologies, we might be able to build a system that can both we can build a system that based on data security agreement and can both make use of data from multi-participants, like gathering data in different locations to gather into valuable knowledge, but also with privacy protection. And that way we can finally reach, which is like maybe our ultimate goal is make data available, but not visible. And basically it can solve the privacy problems of just by avoiding this kind of problems if we can make data invisible but available. So that's all for my presentation, and thanks for your attention and time.
Thank you, Yufeng. Thank you for your presentation. Let me pause.